So Lagrange's theorem. So this theorem states that the order of a subgroup H is the divisor of the order of group G. So if we denote the mod of G, which is the order of G, as n, and mod of H is equal to m, so we get n upon m will always give us some k integer value or a whole number value. And k is also the number of distinct left or right corsets of H in G. So when we implement this in the question, this is the group that we're given, and we have to find out all possible subgroups of G comma dot. Dot is multiplication. So order of G is 4. So all the numbers that divide 4 are 1, 2, and 4. So these are all the orders of the subgroups that are possible. So a subgroup of order 1 can only be 1 because 1 is the identity element and it satisfies all the other properties required to be a subgroup, because 1 dot 1 will give 1 and the inverse of 1 is also 1, therefore it is a subgroup. Now, subgroups of order 4. There are multiple possible combinations, but only this one is a subgroup. This one is not a subgroup because the inverse of I is minus I, which is not present. So this is not a subgroup. Now 1 comma minus I, similarly the inverse of minus I is I, which is not present here. So this is also not a subgroup. This is the only possible combination of subgroups of order 2 that is possible, because inverse of minus 1 is minus 1, inverse of 1 is 1. 1 into minus 1 or minus 1 into 1 both give the values minus 1, which is present, and the identity element of G is 1. So therefore this is a subgroup. Now a subgroup of order 4 is the group itself. There is no other possible combination that's possible over here. So these are all the possible, these three, 1, 2, and 3. These are all the possible subgroups of this group. And this was possible by finding out the order of subgroups that is possible, which is 1 to 4, which we found out from the Lagrange's theorem.